Good day everyone. Today we'll discuss about heat and temperature. When we say temperature, it is a measure of the average kinetic energy of the particles in a substance. Sometimes it is also referred as the hotness or the coldness of an object. So remember the kinetic energy, it is the energy in motion that was discussed on the previous materials or learning materials that I shared. The higher the average kinetic energy, the faster the particles move. So the higher the energy possessed by a particle, the faster it could move or transfer from one place to another. Temperature and heat are not the same thing. So in this lesson, we will talk about the difference, a part of this lesson. Okay, so there are three types of temperature scales. We measure temperatures or temperature in Fahrenheit, Celsius, and also in Kelvin. Okay, so let's start with the Fahrenheit scale. It is most commonly used in the United States, but it originated in the Great Britain. It is a non-metric system scale and not usually used in science. So how Fahrenheit works? Sometimes it is used to describe water's freezing point, and its value in Fahrenheit is 32 degrees Fahrenheit, and also water's boiling point, which is 212 Fahrenheit. Zero was based on the lowest they could get water to stay liquid at the same time. And 100 degrees was based on the highest it was believed human could survive at the time. Now, on Celsius scale, it is based on the metric system scale. Mostly, it is used in the world, including Canada, Europe, and Asia. Just like here in the Philippines, most of the time we use Celsius, even in measuring body temperatures. For example, like right now, we are in pandemic, so most of establishments are measuring your body temperature before you enter their establishment. So as you can see on the thermal scanner, the temperature that is shown is in Celsius scale. So how Celsius works? It works as describing or as a description in freezing point of water, which is 0 degrees Celsius. It's also used in describing the boiling point of water, which is 100 degrees Celsius. Okay, just correction, that is in Celsius, not in Fahrenheit. So the absolute zero is in negative 273 degrees Celsius. Okay, so now let's proceed with the last temperature scale, which is the Kelvin scale. It is the actual or the official metric system scale. It is mostly or often used in laboratory settings for calculation purposes. So most of the scientists, especially those who are dealing with temperatures or in temperature scales, they use Kelvin in describing the temperature of a substance or an object. A change of 1 degree Celsius is equal to 1 Kelvin. Okay, so let's talk about the absolute zero. So when you say absolute zero, it is defined as the 0 Kelvin, or if we go back to the Celsius scale, it is a negative 273 degrees Celsius. It is the average temperature of space is 2.7 Kelvin. Okay, so it is below compared to the temperature in space. So scientists have gotten within fractions of absolute zero, but it is impossible to ever completely stop the movement of an atom, since that means it has zero energy. Okay, so based on the scientists' shared thoughts or opinions, Okay, it is very impossible to completely stop the movement of an atom. Like what I have said earlier, okay, the higher the kinetic energy, the faster the movement of an atom is. So, if an atom is not moving, therefore, it possesses zero energy. And we cannot say that it has zero energy since, well, based on the studies, atoms actually are not moving. Okay, so even if they are staying, for example, so let's recall the potential and the kinetic energy. So when you say potential, it is a stored energy. So even if that object is not moving, or even if it is in place, still there is an energy that is stored in an object. Okay, we have here the temperature scale comparisons. As you can see, 373 Kelvin is equal to 100 degrees Celsius, or the boiling point of water. And in 37 degrees Celsius, which is the human body, or the average temperature of the human body, its equivalent in Fahrenheit is 99 degrees Fahrenheit. And also the room temperature, which is 25 degrees Celsius, its equivalent in Kelvin is 298. The freezing point of water, which is 0 degrees Celsius, is equal to 273 Kelvin. Okay, now let's proceed to heat transfer. So there are three types of heat transfer. We have conduction, convection, and radiation. So let's start with conduction, which is the first type. This takes place between solids or liquids, or again, it takes place between solids or solids with liquids. So as you can see on the figure or on the image, you have their heat, which is started from one molecule or one particle, and this particle will transfer its heat to the nearby particle. So particles vibrating or moving faster transfer some of their energy to nearby atoms. Okay, the other one. Okay, so when particles collide and the faster ones pass some of their energy on to the cooler ones, then this results in a change in energy for its particle. Okay, so for example, we have here one particle that is vibrating or possesses the heat. Okay, so by the way, heat is the energy, okay, stored in one particle. So this particle which has a higher temperature or possesses the heat will pass its energy, or the heat that is stored inside it, it will touch or pass to the nearest particle which has a lower temperature. So this causes the faster ones to slow down and cool. So once this heat or the energy of the hotter one passed to the cooler one, now the hotter one has lesser energy since it already given amount of its energy to the closest cool particle. Okay, so the slower ones speed up and heat up. So since the energy was passed on to the next particle, this particle who received that energy will speed up and will also heat up. Examples of conduction which requires direct contact is, so the first picture we have there is, we have a candle and then you are handling a metal. Okay, so the heat from the fire of the candle will travel on the particles of the metal until it reaches your hand, so that you can feel the energy or the hotness of the particles. Another example is when you touch the stones. So there are geologists or hikers, for example, or people who are studying the rocks. Okay, so these rocks will absorb the heat from the sun. They will absorb it, they will store it, and then later on, when someone passed by and touched the stone, they will feel the warmth of the surface of the stones. Okay, another example, we have here a volcano. Okay, so the warmth or energy stored in the molten rocks or the lava that is flowing on the surface of the volcano. Okay, so from this lava, its stored energy will be passed on to the surface of the volcano. Now on the second type of heat transfer. This heat transfer mostly occurs in fluids like the liquid and gases. It is caused by a change in density due to a change in temperature. Okay, so we have here the image. The fluid cools by losing heat from the surface. So as it cools down, it moves down, and warm or low density fluid rises and the cool high density fluid sinks. So as the air cools down, it becomes, or its density becomes higher, so it will move down. And once the fluid becomes hotter or warmer, it goes up. So the warmer the fluid expands, becomes less dense and rises. The cooler fluid contracts and it becomes more dense and sinks. So for the warmer fluids, since they are expanding, so they become lighter because the particles are moving far away from each other. Unlike cooler fluids, they move closer as they become cooler, so therefore the fluid becomes heavier or denser, therefore it will sink. Lava lumps are an example of convection that you have probably seen before. Okay, so we have here a hot blob rises and the cooler water sinks. Okay, another example. Convection causes warm water vapor to rise, condense into clouds when it cools. Okay, so from vaporization, so the fluid is warmer, so it will go up, forming clouds. And once it cools down, it will move down or falls back as a rain. Without convection, there would be no rainfall and thus no plants. Another example is when magma in the mantle rises due to convection. So the heat from the core hits it and then it rises to form volcanoes on the surface. Okay, so the last heat transfer is radiation. It is the transfer of energy due to infrared and other electromagnetic rays. Radiation can travel through space, so it doesn't need any medium for heat to transfer. All things radiate heat. Like for example here, the sunrise or the sunset, and then we have here the technology. So why are light bulbs hot? Because first, they produce infrared radiation in addition to the visible light, and infrared transfers energy to the molecules that makes them vibrate faster, thus making it hotter. Okay, so here are some of the results for heat transfer. We have thermal expansion. So when an object's heat up, their particles move faster. If there is heat, there is also energy, and once an object receives or has higher energy, therefore the particles will move faster. They hit others harder and bounce further, creating more empty space between the particles. So as they move or bounce against each other and move further from one another, they create a great space, thus resulting to a wide area for them to occupy, thus resulting in expansion. As a result, the entire substance expands. This is known as thermal expansion. Okay, so for example, is the volcano. So again, when due to the Earth's core's heat, the liquid mantle or the liquid rocks will receive more heat, and thus they will expand and will look for an escape. So as a result, there is volcanic eruption. Also on the railroads, so for engineers, they apply this thermal expansion in designing railroads. So during hot summer, for example, so these railroads will exposed to extreme heat during summer, and creating these railroads to expand or change in sizes. So the engineers should apply their idea about thermal expansion in order to avoid accidents. Other examples, roads crack as they expand in the heat. Also, we can observe this in the farms, okay, or in agriculture. On bridges and other sensitive sections, expansion panels allow it to flex. So if you have bridges or a bridge near your house, you can look for this, or on the highways, for example. Okay, so these are used whenever heat is absorbed by the bridge. Okay, so this bridge might expand or contract depending on the changes in temperature. So it will expand during summer and it might contract during cold season, but that is only in centimeters. Okay, so the liquid in thermometer expands as it warms. If you have a thermometer, an old version which has mercury inside, okay, you can observe this. This causes it to heat up or head up the tube and tell you the temperature. Okay, for heat conductors, good thermal conductors transfer heat rapidly, and metals are good thermal conductors. That's why it's very easy to fry or to cook your food using metals. Thermal insulators. So for thermal conductors of heat, they are used in covering our skin during winter or during cold season. Asbestos, the cork, ceramic, cardboard, and finger glass are examples of thermal insulators.